Hello once again, and today we're going to begin applications on the derivative. So we're going to go to the shared screen here. And so our objective today, in your textbooks, it's chapter 4, section 4.1, but the topic here is just dealing with finding extrema, which is maximum and minimum points on an interval. Our objectives today will be to understand the definition of extrema of a function on an interval, to understand the definition of relative extrema on a function on an open interval, and then look at how we can find extrema, extreme points, on a closed interval. Now, first, if we talk about what does extrema mean, all extrema means essentially is just the minimum or maximum points or minimum and maximum values of a function. So if we're looking at the graph of a function, you're just talking about the high and the low points of a function, or the turning points. Now, as it refers to intervals, we have what's called the extreme value theorem, and it simply states that if a function is continuous over a closed interval, then it has both a minimum and a maximum value. That is to say, there's an absolute minimum value and an absolute maximum value. So there's guaranteed to be a lowest value and a highest value. Now here we have a couple of examples of graphs, and it's important that we understand what the conditions are. The conditions are simply here that the function has to be 1, continuous, 2, it has to be over a closed interval. So now, in the case of our first example here, we see that this graph is continuous and it's on a closed interval. We see it because the endpoints we have dark endpoints or filled in circles at the endpoints. So this tells us that this function has a maximum and a minimum. So we see we have an absolute maximum here at the rightmost point. The minimum is at the low point here on the y-axis. In the second example, it's a continuous function, but it's not a closed interval. You can see that from the open circles. So when that happens, here we have a minimum point, but there's no absolute maximum point. Those open circles don't allow for there to be a set maximum value. In the third example, here, it's a closed interval. However, it's not a continuous function because where the minimum would be, we have an open circle. So this function has no minimum, but it does have a maximum value. So now, how do we determine what the minimum and maximum values are for a continuous function over a closed interval? Well, first of all, we have to understand when they can occur in those conditions. So the relative extrema can occur at the endpoints of a closed interval. And those are going to be the case where you have absolute minimum or absolute maximum points. Or they can happen at what we call the critical values. Now, the critical values can occur at turning points or stationary points. Now, this was the case when we look back at our first example on the right. Here, that was a turning point where that minimum was. And note here, if you look at the slope of the tangent line at that point, it would be a horizontal line. So the turning points occur when the first derivative, f prime of x, is equal to 0. Or they can occur at corner points. This would be something that happens, say, for example, for an absolute value function, where you have the V-shaped graph, or sharp corner, or sharp turn. At those points, the derivative doesn't exist. So we want to examine what the critical values are in a closed interval for a function, because those are points that could have extreme points. Now, relative extrema only occur at critical numbers, although not all critical numbers may end up being relative extrema. So you want to determine what the critical numbers are, and then from there, make the determination as to whether they will be extrema, whether or not they will be extrema. All right, so now let's look at an example to get an idea of how we want to go about doing this. And so our goal here, first of all, for our example, is to find the extrema of the function f of x equals 3x to the fourth minus 4x cubed on the interval from -1 to +2. So now what we're going to do here is we're going to look at, first of all, identify the endpoints. Secondly, we're going to identify the critical points. And then, because those are all the points, the endpoints, the critical points, those are the points where the highest and lowest values could occur. So once we find out what those points are, then we're going to test each of those points against the function to find out which is going to be the maximum, which is going to be the minimum. Now, it should go without saying that this function, being a polynomial function, does satisfy the conditions of the extreme value theorem because it is a continuous function. Polynomial functions are continuous over their entire domain. And we have a closed interval from -1 to +2. So now let's take a look. And let's switch over to the whiteboard. All right, so remember that our function f of x equals 3x to the fourth minus 4x cubed, and the intervals from -1 to +2. All right, so now let's look at the endpoints. So now the endpoints are simply -1 and +2. So x equals -1, x equals +2. Those are the endpoints of the interval. So now we find the critical points or the critical values. So now for the critical values, we find the derivative f prime of x, and then we're going to set that equal to 0. All right, so now if we find the derivative, well, the derivative, we have a polynomial function. The derivative here is going to be 12x to the third minus 12x squared. And so then we take that derivative and set it equal to 0. All right, so this we can factor. So we have a common factor of 12x squared times x minus 1 equals 0. And we set each of the factors equal to 0. 12x squared equals 0. X minus 1 equals 0. So it should be pretty easy to see that we'll have x equals 0 and x equals 1 as our critical values. So these are the values where the derivative is equal to 0. Now, being a polynomial function, there are no points where the derivative is going to be undefined. So we don't have to worry about that. So now we have 4 critical points, the endpoints and the critical values. So now what we're going to do next is we're going to take each of those values -1, +2, 0, and +1, and we're going to test them up against the original function. So now if we test it against the original function, we plug each of these x values, plug each of the x values into the original function. So for -1, that'll be 3 times -1 to the 4th minus 4 times -1 cubed. So that'll give us 3 plus 4, which is equal to 7. So when x is -1, f of x is going to be equal to +7. For +2, this will be 3 times 2 to the 4th power minus 4 times 2 cubed. So 3 times 2 to the 4th power, that's going to be 48 minus 4 times 8, which is 32. That's going to be equal to 16. At 0, this will be 3 times 0 to the 4th power minus 4 times 0 cubed. So that's just going to be equal to 0. And then at +1, 3 times 1 to the 4th minus 4 times 1 cubed, which is equal to -1. So now when we look at this, so now we look at our values, all right, and we're going to do a quick double check to make sure that our values are correct. All right, so now when we look at the y values, notice here that the greatest of the y values we have is at 16. So that's going to be our maximum. And then the lowest y value is -1. So that's going to be the minimum value. All right, so now when we answer the question as to what the extreme points is, we would say that the absolute maximum is equal to 16 when x is equal to 2, and that the absolute minimum is -1 at x equals +1. Now, one of the good things about this is that this is something that we can verify when we look at the graph of the function. And so if you have access to a graphing calculator, you can graph the function out, and you'll indeed see that these will be the minimum and the maximum values. I can draw out a sketch of the graph. And trust me, this will be a very, very rough sketch. All right, so In this particular instance, we're looking at the interval from -1 to +2. Okay, and so we can sort of see in a rough way here at -1, that was one of the endpoints. +2 was the other endpoint. We can see at +2 how that's definitely going to be a maximum point there. And our minimum point occurred at x equals 1, which is here. And it's a good idea to utilize your graphing calculator and use it sort of as a confirmation to the values that you get when you work them out this way. All right, so now what exactly did we do in this process? Well, what we did here is the same thing we can do for finding extrema for any closed interval. All right, so if we want to find the extrema of a continuous function on a closed interval, first of all, you do want to make sure that those conditions are indeed met. You have to have a continuous function and it's got to be over a closed interval. So then what do? We find the critical numbers of the function on the open interval from a to b. And we just basically do that by setting the derivative equal to 0 and solving it for x. And then also identifying anywhere where the derivative is undefined. So those will give the critical values. So then we evaluate the function at each of the critical points that we find. Then we evaluate the function at each of the endpoints because those are the points where the absolute values can occur. Now, once we do that, the least of the y values that we have is going to be the minimum, and the greatest of those y values will be the maximum. Pretty straightforward. Let's look at another example. Here we have the function f of x equals 3x to the 2/3 power minus 2x on the interval from -1 to +1. So let's go back to the whiteboard. All right, and so now let's begin with our function. All right, so we'll start by, we have the endpoints, -1 and +1. So that part's done. The other part that we have is that we want to find the critical values. So we find the derivative, so f prime of x. So in this case, that's going to be equal to 2x to the -1/3 power minus 2. And so now we're going to set this equal to 0 to find the critical values. Now, remember that this power, x to the -1/3 power, is equivalent to saying 2 over x to the +1/3 power, or simply 2 over the cube root of x. Now, I choose to write it this way so that we can see one thing that is apparent. We are going to have a critical value at x equals 0. Because we have x in the denominator, if x is equal to 0, you'll have division by 0, and so that's undefined. So we can make a note that f prime is undefined at x equals 0. So that's going to be one of our critical values right there. Now, we still need to solve the equation. All right, so let's go about the process of solving this. So now we can add 2 to both sides of the equation. And we'll multiply both sides by the cube root of x because you want to be able to clear out all the fractions. So if we do that, we'll have 2 equals 2 times the cube root of x. Divide both sides by 2, and we have 1 equals the cube root of x. Cube both sides, and we'll end up with x equals 1. All right, so we have a critical values at x equals 0 and x equals 1. Now note here, x equals 1 does also happen to be one of the endpoints, and that's okay. Sometimes that happens. It's no big deal. That actually saves us a little bit of time because we don't have to, with one of the critical points being an endpoint, we can kill 2 birds with 1 stone and test them both at the same time. So now that we found the critical points, we have the endpoints. We do just as we did before. Test our values. So the endpoints, -1 and +1, which is also a critical point, and then x equals 0, which is a critical point. And we're going to plug this into the original function, 3x to the 2/3 power minus 2x. All right, so now let's plug these values in. All right, so for -1, you have 3 times -1 to the 2/3 power minus 2 times -1. So -1 to the 2/3 power, that's going to be equal to +1. So it'll be 3 plus 2, which is equal to 5. At +1, we'll have 3 times 1 to the 2/3 power minus 2 times +1. So that's simply 3 minus 2, which is equal to 1. And at 0, 3 times 0 to the 2/3 power minus 2 times 0. Okay, should be easy to see that that's going to be equal to 0. All right, so just doing a quick check. Make sure there's no problems here. So at -1, +1, and 0. So everything works out just fine. And so now, what do we have? +5, that's our greatest y value. So that's going to be our maximum. And then 0 is going to be our lowest y value. So that's our minimum. And so to answer the questions here, we have an absolute maximum, which is equal to 5 at x equals -1. And then we have an absolute minimum, which is equal to 0 at x equals 0. All right. So there you have the basic process. The one thing or a couple things to keep in mind is make sure that you examine the function both at the endpoints of the interval and the critical values. And also, when determining the critical values, remember, set the derivative equal to zero, but also look for any values where the function's undefined. And that's going to be kind of tricky because it can be kind of easy to miss. Look for functions, in particular functions that are rational functions where you have the variable in the denominator, or you have something that may contain square roots, anything where you may have an undefined result or where the function may not exist. Those are going to be some candidates. Um, there's going to be points to look out for um, where the derivative is going to be undefined, and those are also going to be critical points as well. All right, so once you do that, you should be fine. All right, so that does it for this particular topic. In the next topic, we're going to look at Rolle's theorem and the mean value theorem, which also gives us some more information about functions and their derivatives. So we'll get into that into the next session. All right,